Hi everyone, I'm glad you're back for part 4 of the All About the Periodic Table video series. We are going to go over trends of the periodic table. And these are very important because not only does the periodic table tell us the atomic numbers, the atomic masses, and all sorts of things that are of value to chemists, but there's also trends within the periodic table that are important. One of the first things, and we kind of hit this on last video when we talked about valence electrons. Okay, and these are the number of electrons in the outermost energy level of an atom. And for our representative elements, group 1A through 8A, basically the number of valence electrons is equal to the group number. So the group number gives the number of valence electrons for the representative elements. And here that's the only thing that we're really worried about for the purposes of this class are the representative elements. Okay, and so if we look at the periodic table, so here are our group 1A, 2, and then we skip all over here, 3, 4, 5, 6, 7, 8. Okay, and so the group number corresponds to the valence electrons, and so these electrons are the most important electrons in the atom, and that's because they're the most accessible. They can react and they can form bonds, they can react with other atoms, and so on. So if we look here, our group 1, anything in this group is going to have one valence electron. And if you remember, whenever we came up with the electron arrangements for atoms, we had here, for instance, we would have for, let's say, lithium, we would have a 2 in the first energy level and a 1 in the second. And so it had one electron in its second energy level. So it's in group 1, it has one valence electron. Okay, group 2, it has 2. So if we were to just pick some, so let's say phosphorus, all right, it is in group 5, so it's going to have 5 valence electrons. If we pick, let's say, cesium, it's here, it's in group 1, so it has one valence electron. Okay, if we pick krypton, in group 8, it has 8 valence electrons, so it has a stable full octet because it has all of its electrons in its energy level. Okay, for carbon, so here group 4 has 4 valence electrons. Group 3, so let's pick gallium. It has 3 valence electrons because it is in group 3. Okay, so this shows us here group 1 has 1 valence electron and so forth. Okay, the next thing we're going to talk about with respect to trends of the periodic table is if we move down the periodic table, the size of the atom or the atomic radius increases. And this makes sense to us because as our energy levels are growing, right, so we're getting more and more energy levels surrounding the nucleus, so it makes sense that as we move down that the atom is getting larger, okay? However, as we move across, even though our atomic number is increasing, the size of the radius decreases as we move across. Okay, and so fluorine, neon, helium, these are our smallest atoms. Okay, the reason for this is because if you think about the nucleus, it's positively charged. And the more electrons that you have, so as you move across, you're increasing in atomic number. Okay, so it's like 3, 4, okay, so we keep moving over, 5, 6, 7, 8, 9, 10. Okay, so we're increasing in atomic number. So you might think, well, wouldn't you increase size? But you're increasing in electrons. Remember that electrons basically have no mass that is relevant. And so what you're doing is you're increasing the negative charge that surrounds the nucleus. So the more negative charge, and your nucleus is positively charged. So if you think about a magnet, if you have a negative end and a positive end, they're going to attract. So it's just like a magnet. You've got negative, positive, they're going to want to be close to each other. And so the more negative charge you have, then the more attraction there is for the nucleus Therefore, it almost, in a sense, is, not shrinking, but it's making the radius smaller because there's more attraction there for the nucleus. So our third trend, so we've talked about valence electrons is equal to the number of, or the group number. We've talked about atomic radius. So as we move across the periodic table, we decrease in size, and as we move down, we increase. Now we're going to talk about ionization energy. Okay, this is the energy required to remove one of the outermost electrons from an atom. Okay, so how much energy does it take to take away an electron? So here we have sodium neutral. We remove an electron, which gives it a positive charge because an electron's negatively charged. So if you remove it, then it's going to become more positively charged. So this trend, the ionization energy decreases down a group, but increases across a period. Okay, so if we look here, ionization energy is decreasing. So it takes less energy as you go down the periodic table for an electron to be removed. And it increases as you move across. So it takes more energy to remove an electron. Okay, so ionization is the energy to remove an electron. And this will make more sense later, but just briefly I'm going to try to explain this, is that your metals here, okay, everything wants to be like the noble gases. Okay, so a metal, in order for it to have a configuration like a noble gas, metals want to lose electrons. So metals want to lose electrons, which means they're going to form a positive charge because they lose a negative charge. Okay? But your nonmetals over here, they want to gain. Okay? They want to gain. So here fluorine is only one electron from being like neon. So it wants to gain an electron because if it gains one, then it has a configuration like neon. Okay, so it takes more energy to remove because nonmetals don't want to remove, they want to gain. So nonmetals want to gain electrons, not lose them. Okay, so that's why, if you want to think of it this way, so cesium would be, on this chart, would be the lowest ionization energy. So the lowest energy. Okay? Reasoning for that is it's a metal. So remember our metals are on the left of the stair step, nonmetals on the right. It wants to lose an electron. So it doesn't take as much energy to lose it. Okay? And also, as it gets larger, so cesium is larger, has more shells, energy levels, and so those electrons are even more accessible to be removed. An element with metallic character is one that loses electrons easily. Okay, so we just talked about this. So metals want to lose electrons to be like the nearest noble gas. Okay, and so obviously on the left side of the periodic table are your metals, and so on the left side there's going to be higher metallic character. Okay, so metallic character is more prevalent in metals on the left side of the periodic table and less for the nonmetals on the right side of the periodic table, because nonmetals, they want to gain electrons for the same reason, to be like the nearest noble gas, to have an electron arrangement like the nearest noble gas. So this should make sense. So if we move from left to right, we're going to decrease metallic character, right? Because we're moving towards our nonmetals. Okay? So our more metallic character is going to be over here with our metals. Okay, and then metallic character is also going to increase as we go down. Okay, so as we move down, so once again, so on the previous slides, about ionization energy, cesium had the lowest ionization energy. And that's because it wants to lose electrons. So for the same reason, it has the highest metallic character, because metals want to lose electrons. Okay, so as you move from left to right, you're decreasing in metallic character because you're moving towards nonmetals. And then you're increasing as you move toward down because the energy levels are larger, more accessible, and you're increasing the metallic character. Okay, so here's a little summary of these trends. So your valence electrons are just equal to the group numbers for your representative elements. Your radius increases as you move down and decreases as you move across due to the increase of protons in the nucleus that pull electrons closer. Ionization energy decreases from top to bottom of a group and increases left to right across a period. And for metallic character, it increases top to bottom, so down towards cesium has the most metallic character, and it decreases as you move from left to right because you're moving towards nonmetals. In Chapter 4, this is a little preliminary, but I want to go back really quick and talk about one more trend that is super important, actually one of my favorite things to talk about, and you'll get into it more in Chapter 4. But this is electronegativity. Okay, and this means, or is the ability, so it's the ability of an atom to attract electrons to itself in a bond. Okay, and so this becomes really important with bonding, but I want to go ahead and discuss it because it is a trend and it's super, super important. And you'll also learn that electronegativity, if I can talk here, it parallels with polarity, okay, how polar a bond is. Okay, so how I like to think about this, if I had, I guess if I had a better video where it could get me moving around, you could see that I like to demonstrate this as kind of a tug-of-war effect. Okay, so if an atom can pull or attract electrons really hard to itself, then it has a higher electronegativity. So if you think about it, it's like it's winning the tug-of-war, or it's an electron hog. Okay, so it's pulling those electrons towards itself away from another atom. And the most electronegative element is fluorine. So En stands for electronegative. Okay, it is the most electronegative element. So anything, if you move away from fluorine or you move down from fluorine, then it's going to become less electronegative. Okay, and once again, electronegativity is the ability for an atom to attract electrons to itself. And this becomes really important when we have bonds and when we're bonding, because if we have, let's say, a hydrogen and a fluorine bonded together, okay, and here we've got two electrons that make this bond, and if fluorine is the most electronegative element, actually has a value of 4.0 for its electronegativity, and it's a electron hog. It wins the tug-of-war, okay? And so it actually bears, these are partial signs, a partial negative charge because it's pulling the electrons towards itself, and it is essentially it's gaining that electron, or it's not completely gaining it, but it's the distribution here is uneven. Okay, it's winning the tug-of-war on the electron, and since electrons are negatively charged, it gets a partial negative charge. Okay, and we call this a polar covalent bond. Okay, so when you get to this in Chapter 4, when it's talking about polarity, okay, it really is just talking about electronegativity. What's the difference? So if you have a larger difference, or change in electronegativity, then the more, I'm running out of room here, the more polar. So hopefully this will help you when you get into Chapter 4. But this concludes the videos for Chapter 3, all about the periodic table. Thank you.